Exercise 1826 is trying to see if you can recognize benzene rings using the different types of spectroscopy. So in IR spectroscopy, you're shining infrared light onto the molecule, and the molecule absorbs the light. Different bonds will absorb different energy light, different frequency light, when they start vibrating in new ways. Now, two shadows that are cast in this type of spectroscopy is an sp2 hybridized carbon to hydrogen bond. That happens on benzene, so that's that bond right there, because each of the carbons in benzene is sp2 hybridized, and so you have those bonds to the individual hydrogens. And those appear around 3100. Now in this case, because these are technically not double bonds, all of these are somewhere in between a double bond and a single bond, because all of the electrons that are in those, what are drawn as double bonds, spread out, move around the ring, so that each of the bonds is something like 1.5. Because of that, this spring is not quite as strong, and so it doesn't take quite as much energy to make it vibrate. And so sometimes you'll see it a little bit below that, so somewhere in like the 3000 50s, or something around there. So I'll emphasize that around approximately 3100 for benzene. And the other benzene, the other feature that you'd see in an IR spectrum for benzene is between around 1450 and 1650. And these are wave numbers, the units for these. Just a unit that's corresponding to the amount of energy of the light that you're shining on them. Around between 1450 and 1650, that's where you have the sp2 hybridized carbon to another sp2 hybridized carbon bond. That will vibrate in a different way when you shine that energy of light on it. So that would be like these bonds here. Excuse me, between the carbons in the benzene. So those are two pretty typical features of a benzene ring. Note that if you see something above 1650, then it's probably the carbonyl. So a carbon to oxygen double bond, that's around 1700. If you get something like 1680, that's not in this range for the carbon to carbon sp2 bonds, the sp2 hybridized carbon to carbon bonds. That's more likely to be the carbonyl. So those are some features to watch out for in the IR spectrum. And then in the NMR spectrum, we've seen that benzene shows up between 6.5 and 8 parts per million. Oops. It's the only thing that has signals there, and you would look at the integration to tell how substituted the benzene ring is. Benzene all by itself normally has 6 hydrogens, one at each of the carbons. If it has one branch, then it would only have 5 hydrogens. If it has 2 branches, then 4, and so on. So you can tell the number of branches you have based on the integration. Lastly, if you have a di-substituted benzene ring, you can get some information from the carbon-13 NMR spectrum. But we'll look a little bit more at that in the next exercise where they give that information to you. But we'll keep that in the back of our minds. We can get some information for how those 2 branches, if you have 2 branches coming off of a benzene, you can get some information about how those are arranged using the carbon-13 NMR spectrum. Okay, so whenever you're given these spectroscopy problems, look at the molecular formula. Remember, you would get that molecular formula from mass spectrometry. You'd compare the molecular ion peak to the M+1 peak, and based on the ratio of those, right, for every carbon, this is 98.9% chance, for 98.9% of the carbon in the world is carbon-12, 1.1% approximately is carbon-13. Oops. And based on the ratio of those, you can tell based on how much carbon-13 you have, you can tell how many carbons you have in the molecule. So if you only have one, then this M+1 peak, it'll have one more mass unit because of the 13 rather than the 12. That'll only be 1.1% as high as the carbon 12 peak, the molecular ion peak. If it's 2.2, then you'd have 2 carbons. If it's 3.3% as high, 3 carbons, and so on. So you can use that mass spectrometry to get the molecular formula. Once you have the molecular formula, which they usually give you in these problems, the first step is always to find the index of hydrogen deficiency. That tells you how many pi bonds or rings that you have in the molecule. And that's 1/2 times the number, 2 times the number of carbons, plus 2, plus the number of nitrogens, minus the number of hydrogens, minus the number of halogens, so like fluorine, chlorine, bromine, and iodine. So here that's going to be 1/2 times we have 8 carbons, so 2 times 8 is 16, plus 2, we don't have any nitrogens, we have 8 hydrogens, and we don't have any halogens, so that's 18 minus 8, or 1/2 times 10, which is 5. So we have 5 degrees of unsaturation. And if you have 4 or more degrees of unsaturation, that's a strong sign that you have a benzene ring. So already we're thinking, okay, probably a benzene ring, but also notice benzene only has 4 degrees of unsaturation. You have the ring, that's 1, and then you have 1, 2, 3 pi bonds. So altogether that's 4. Here we have 5. So in addition to the benzene ring, we're either also going to have another ring or another pi bond. First, and here I'll, just to make room, make this a little smaller. So we have 5 degrees of unsaturation. So we're thinking, okay, maybe we have a benzene ring here. What can we look for to confirm that? Well, in IR spectroscopy, we would be looking for 2 things. First, do we have a signal close to 3100? It might be a little less. And we do have that right here. And second, do we have a signal between 1450 and 1650? That would represent the carbon-to-carbon bonds in the benzene. And we do have that. So the chances that we have this benzene ring are now getting extremely high. Next, this aromatic benzene ring. The other way you can confirm it is by looking at the NMR spectrum. Do we have a signal there between 6.5 and 8? And we do. We have a multiplet at around 7.5. So we definitely have benzene. All signs are pointing to benzene. So the next question is, how many branches are going to be coming off of the benzene ring? And for that, you look at the integration in the NMR spectrum. You can see that the benzene ring, the signal coming from between 6.5 and 8, so here's 7.5, that's the benzene ring. That has 5 hydrogens on it. And that, now normally, benzene would have 6, 1 on each of the carbons, 6 hydrogens. But if you're going to have a branch, you have to get rid of one of those to make room. And so you'd only have 5. So if you have 5 hydrogens on a benzene ring, that means you have just 1 branch. So already this is going to be one of our puzzle pieces, a benzene ring with 1 branch. Now keep in mind we still have another degree of unsaturation to account for. And we also have other information from the NMR spectrum and from the IR spectrum. If you look at the IR spectrum, so we've already taken into account this 3063, that's the carbon to hydrogen bonds in benzene. We've already taken into account the 1646, that's the carbon to carbon bonds in benzene. We still have this 1686, which is close to 1700, and that is going to be a carbonyl. So if it's above 1650, that's the cutoff for the benzene, then it's going to be a carbonyl. So here we probably have this carbonyl here. Now that carbon only has 2 bonds, it's going to need 2 more. So already we're thinking, okay, this is going to be in the middle of the molecule. The benzene has to be on the end because it only has 1 branch, and this is going to have to be in the middle somewhere. Okay, well, so much for that. Next, we've taken into account the multiplet with the benzene signal that we're getting from NMR, And we just have one more signal. Now this is a singlet. That means that there can't be any hydrogens nearby. There are 3 hydrogens being represented by the signal, and that, the only way you could really have that with the pieces we have left is a methyl group. Because notice, we've already used 7 carbons. We used 6 in the ring and 1 in the carbonyl. We only have 8 total, so this must be a methyl group with 3 hydrogens on it. Now, normally a CH3 would be at around 0.9 parts per million. This is almost 1 higher than that, and so it makes sense that this would be next to a carbonyl, because if it's alpha to a carbonyl, you'd add 1. It's not perfectly 1, but it's pretty close. Finally, it's a singlet, so there can't be any hydrogens nearby, so you wouldn't be able to attach this methyl group directly to the benzene ring. Actually, in that case, you still would get a singlet. Sorry, but that's another confirmation that you would have. You would have this. It'd be okay for that carbonyl, carbon double bonded oxygen, to be nearby. The reason why you couldn't put this directly to the benzene ring, though, is because this only forms 1 bond. The benzene ring only forms 1 bond. If you put those together, there's no place to put the carbonyl. The carbonyl is the only thing that can form 2 bonds, so it has to be in the middle. And so this would give you a singlet. All of these 3 hydrogens are in 1 electronic environment. A singlet that would be shifted downfield because it's alpha to this carbonyl. And it would have 3 hydrogens in it. And the reason why this is probably not being shifted at the full 1 part per million downfield is because of the magnetic anisotropy of the benzene ring. But okay, so that's all the information for that. You put those 3 together and you get your final molecule, which would be that beautiful thing right there. So we followed that normal procedure. We used the index of hydrogen deficiency first to see the degrees of unsaturation, and then we watch out for key things in the IR spectrum and in the NMR spectrum that would let us know there's a benzene. We figure out the number of branches on benzene, and we use the rest of the materials and the splitting pattern